we come to some questions of, some deeper questions of performance. The high level question is, how long does it take me to access, reads and writes are typically symmetrical. How long does it take me to access disk? That's my high level question. Well, how much disk do we need to access? We are accessing some number of sectors. So let's start simple, one sector. Access one sector. So how long does it take me to access one sector, to read or write one block of information? Number of sectors in my access is a parameter. If it's one, that's going to make my life a little simpler for now. So let's break down what happens with one sector. CPU initiates the request. I'm actually generally going to ignore that cost. If it's a write, the CPU has to send that data. We're going to count that because it's 4,096 bytes. You don't get that for free. Our data send. And if it's a write, that's going to be the first thing coming. If it's a read, that's going to be the last thing that happens. But we can count it whenever we want because we're just doing additions. So we're going to call this the bus transfer time or something like that. So the bus transfer time, just like with the memory bus transfer time, the CPU disk bus transfer time depends on the bus bandwidth. So let's say 1 gigabit per second is my bus bandwidth. So my bus bandwidth, 1 gigabit per second. Now, unfortunately, sadly, historically, gigabit per second uses the SI prefix giga of 10 to the 9th, not the computer science prefix of giga 2 to the 30th. So 1 gigabit per second is equal to 10 to the 9th bits per second. If we have to transfer 4,096 bytes, how long does that take us? Here's our first math question. And I'm actually going to show you how to do that. Isn't that novel? Okay, so we got to get our units to be the same. Since I got a power of 10 here and not a power of 2 here, I'm going to make my units bits. So I'm going to take 4,096 bytes, and I'm going to convert that to bits by multiplying it by 8. Well, that's 2 to the 12th. We know that, right? 2 to the 12th bytes times 2 cubed. That's 8. So 2 to the 15th, right? Bits. With me? So I'm transferring 2 to the 15th bits, and I can do it 10 to the 9th bits per second. So I take the amount of data I want to transfer, and I divide it by my bit rate. So 2 to the 15th bits divided by 10 to the 9th bits per second. And that's going to cancel out my units there. And per second comes up there is going to give me 2 to the 15th divided by 10 to the 9th seconds. That's my answer. Okay, so we've got this amount of time. That's how long it takes us to transfer a block. So that is our bus transfer time, or our bus access time. So we'll start with that. And then we're going to add to that some more stuff. Figure out how long it takes us to access. Plus, all right, what comes next? We're going to pay our average seat time. That number has to be given to us because that number depends on the speed of this arm moving, which depends on the motor that's moving it. We have no way of calculating that. We have to be told this is how fast the arm moves. So we're given the average seek time, and maybe we're given it as, I don't know, let's call it 5 milliseconds. Because it takes time for that motor to move that arm precisely where it has to go. Here, our first term we had here was our bus access time. So now we're going to add our seek time. Before we add our seek time, we may, in some of our formulations, have an overhead to pay for our control logic, because that takes time too. So we may be told the controller overhead is some amount of time. It's usually going to be pretty minuscule, but it may exist. So we have our seek time of 0.005 seconds. I just took my milliseconds, put it in seconds. It's fine. It's all good. Now, of course, you have to put it in whatever I tell you should put it in. I think I asked for milliseconds. I'm going to drop a line here and go plus. And we'll also do that here. Plus. All right. As we seek, we actually hide the head switch time if it's smaller. So let's say our head switch time is 2 milliseconds. As we're seeking, 5 milliseconds is more than 2 milliseconds, we're going to hide it. If it was the other way around, the head switch time might be hiding the seek time. It's really, really not likely to happen. But that seek is a really timely thing. It takes a lot of time for a motor to move an arm. So that head switch time is hidden by this, right? So it's seek time and the head switch. Now this is under the assumption, by the way, that the disk is not already at the sector track I want, rather, it's the track I want. If the disk is already at the track I want, then I wouldn't pay it, but I'm going to assume one sector at some random location. So seek gets us over the track we want. Head switch gets us to the surface we want. Now we have to wait for the disk to spin for the sector we want to pass under the head. On average, that's going to be 1/2 rotation. Randomly, we don't know where we'll be, which sector will be over when we arrive at the track. So if it's uniformly random which sector number we want to access, then on average, we have to wait for 1/2 of a rotation. It could be the very first sector, but it could just as easily be the very last sector. It could be the second sector, but it could just as easily be the second last sector. First sector, the last sector equally likely, that's 1/2. No probability, you probably passed a discrete math class by now. If you didn't, just take my word for it. It is 1/2 of a rotation. How long is a rotation? Figure that out. For that, we need to be given what the RPMs are. So I'll do 5,400. 5,400 RPMs. I'm not gonna do the one I asked you to do. Okay, I probably could do it, but so if we got something that's spinning at 5,400 revolutions per minute, I want to calculate one revolution, and I want it in seconds. So the time it takes for one revolution is just the inverse of this, right? 5,400. So it's 60 divided by 5,400 to get the number of seconds per revolution. So let's work that out real quick here, because some of you didn't get it, some of you did. 5,400 revolutions in 1 minute. I want to invert it, so I'll just flip it over, right? So it implies 1 minute per 5,400 revolutions times 1 minute per 60 seconds. Work that out, I'll get 60 over 5,400 seconds per revolution. So one rotation, 60 divided by 5,400, half a rotation takes half of that. So 60 divided by 5,400 divided by 2. That is the average rotational latency, 1/2 of a revolution. So my average rotational latency or delay. So now the sector I want to access is passing the head, and I access it. And that takes however long it takes for a sector to pass by the head, which is a fairly minuscule amount. But for that, we need to know the average number of sectors in a track and calculate the portion of a track, the fraction of the track circumference, I guess it would be the right word, is that circle, that would be that number of seconds, right? So let's say there are on average 100, suppose this is 100 sectors per track on average, then on average, the average transfer time for a sector to transfer between sector and the disk controller's memory, one rotation divided by the average number of sectors. So we take again this rotational, the full rotation, which is 60 over 5,400. That's our full rotation. And then we divide that by the average number of sectors. So times 100 in the denominator. That is our average sector or block transfer time it takes for the sector to pass under the head. We're done. We've counted everything. If it's a write, we pay this bus access up front. If it's a read, we pay this bus access on the end. So that's for one sector. Now we want to access 2 sectors. If we want to access 2 sectors, now we have to know, okay, at a random location, in that case, we're going to seek to the new track, because it's random, so we can't assume it's on the same track. So we assume we pay the average seek time. We're going to pay the average rotational delay, and we're going to pay to transfer that to the disk controller. Most likely, this bus access time is hidden by this seek, rotate, transfer time, which means we only pay for one of these bus accesses. If it's a write, we pay for the first one. If it's a read, we pay for the last one, because the other ones are hidden by us accessing the disk, which means this comes out to multiplying this cost by 2 with a single bus access. But you got to confirm that the bus access time is actually less than this. Now I know it's less than this because that's 5 milliseconds, and this is much less than 5 milliseconds. What if it's not at a random location? That's where all those exercises and examples that you do. So if it's on the same track, you don't have to seek. You just gotta wait for it to spin, wait for the disk to spin, and for the head to pass under it again. If it's on the same track but in a different surface, you gotta do a head switch. And then you gotta wait for it to rotate. The head switch time is hidden by the seek time only if you do a seek. If you don't have to do a seek, you probably have to pay for a head switch, assuming you have to access a track that's on a different surface. If you access the same surface and the same track, then you just pay for disk spinning time, however much time it happens to need. And that depends on the layout of the sectors you're accessing in the disk. So now we're going to come to the very last little tricky, perhaps, but hopefully not, mental block that students tend to have, which hopefully is addressed through the examples. Everyone have a piece of paper? Sure. Or something. Put your finger on that something, right in the middle. Okay. Now, spin it clockwise. Just make sure you can spin it clockwise. Now, pretend, put your finger there. I know it's hard. Or a marker, and think about, as you're spinning it clockwise, just spin a little bit. How is your finger as the head? How is the track passing that head? Counterclockwise. The order of the sectors is optimal in the opposite direction of the spinning. But wait, there's more. Pick up your spinning thing and spin it clockwise from the top. Which way is it spinning on the bottom? Keep spinning it and turn it over. Keep spinning it and turn it over. It's spinning counterclockwise when you look at it from the bottom. Which means the optimal layout of your sectors on the bottom is actually clockwise. So if your sectors are laid out clockwise on the bottom surface of a platter that's spinning clockwise from the top, then you can access those sectors consecutively, one right after the other. I think that we're good as far as that goes. We're going to cover dependability topics, which is the last part of the homework, next time. Goodbye, Zoom. Hope you followed that paper spinning thing along at home.